So today we're going to do some support vector machines, or SVM. So we're going to import some NumPy, pandas, and some sklearn packages. And we're going to do SVM from scratch first. So we're going to make some blobs. X comma y equals make blobs 100 samples, 2 centers, and random state 42. And then where y is equal to 0, we're going to comport it to -1. Otherwise, it's going to be 1. So here we're going to print x. And recall, it's just 2 columns. Yeah, just 2 columns of different numbers. And then we print y. And we have 3 separate classification labels. And then we do class SVM. So we have our learning rate. We have our lambda parameter. We're saying our learning rate equals to 0.001, lambda parameter equals 0.01, and number of iterations equals 1,000. We have no weights and no bias, and then we're just going to train that. So recall, support vector machines is a linear separator. We're basically going to be separating separating the different classes by drawing lines in the in theoretical space, in this case 2D space, to separate our classes. So here we have a number of samples, number of features, equals x.shape, and then so we have a set of weights we initialize to 0, we have a bias that we initialize to 0, and then we basically create, because support vector machines, we find the maximum separating margin, where we separate the classes from the line with the maximum amount. So we find the lines that separate the classes smoothly. So then here we initialize an sklearn SVM model. Here we fit the data of the sklearn SVM model, make our predictions, and we get the accuracy 33%. Not particularly phenomenal, but it's okay. Apply the decision boundary, and here we go. It's kind of low. Let's try that again. Oh, now one, seems like we did that with a different set of values. And here we go. We have a clear boundary that separates the red from the blue using, basically by maximizing the distance here and the distance here, maximizing the distance to the closest values. Now we load the iris data set. We perform train split, test split. Test size equal 0.3, random state equals 42. We create a linear kernel with an SVM. We do the fits. We create the predictions. Put the confusion matrix. Recall the confusion matrix. This center value, this diagonal, is the number that predicted correctly. And then this off-center is how much is predicted to in one class it's in another class. So we get precision recall F1 score for each of the classes with each other. We also get the macro averages, macro F1, macro recall, macro precision, the weighted average. And now we plot the decision boundary. Here we go. We've separated into 3 different classes based on the boundaries. And notice there's some of one class in the other boundary. And now let's see if we can do it a little bit better by using a radial basis function. So what basically a radial basis function does is it transforms via the kernel trick to something that looks a lot like a normal random variable. It's a normal random variable So there we are, a normal random variable, and we convert there, and when we do the fit for the SVM trained with a radial basis function, so then we predict, then we print the confusion matrix, print the classification report, and then we plot the decision boundary. So confusion matrix doesn't look like we're doing a lot better, not really any better. And here, let's see, same 80% accuracy, but we have a decision boundary that's a little bit more curved, and it's nonlinear now. So this is good when you have a little bit of nonlinearity. All right, that is code for support vector machines, and I hope you have a great day. Thank you. Bye.